In life, choice guide almost everything we do, and in-situ bioremediation is built on the same principle. There are many ways to clean contamination directly in the ground. Bioventing supply oxygen for natural breakdown. Biosimulation boosts microbioactivity with nutrients. Bioaugmentation introduces new microorganisms to make the process faster. Bioattenuation let the nature take over its own pace. And permeable reactive barrier trap and treat pollution below its surface. Each option brings its own strength and gives us a smart and flexible approach to heal the environment. In this video, we will look into further on the implementation of each in-situ bioremediation technique.
Our planet faces constant environmental stress, but did you know nature often has its own internal repair kit? Today we explore bioengineering, the most passive yet powerful form of bioremediation. Bioengineering, also known as natural attenuation or intrinsic bioremediation, is a passive approach where nature is allowed to heal itself after the source of stress is removed. The primary goal is to treat contaminated soil or groundwater by using the metabolic activity of native indigenous microorganisms. It is often termed as the do-nothing approach, but in reality it is scientifically monitored process of degradation.
Moving to the next part, the method of this process relies on natural mechanisms, including aerobic and anaerobic biodegradation, sorption to soil particles, volatilization, and chemical stabilization. So, the configuration of this process is strictly in situ, meaning that treatment happens directly at the site without excavation. It requires constant monitoring of dissolved oxygen and carbon dioxide levels to ensure activity. For example, consider the Exxon Valdez oil spill case happened in Alaska 1989. Studies showed that indigenous microbes often outperformed artificial bioaugmentation because they have a learned resilience to the local toxins.
Bioattenuation offers several important advantages in environmental remediation. Firstly, it is cost effective by reducing the need for expensive engineering treatments. Next, as a non-invasive in situ method, it requires minimal surface disturbance and allow normal site activities to continue. At the same time, it also minimizes waste generation and lowers risk linked to excavation and contamination transport. Other than that, by relying on the natural microbiome process, and biointerventions provide an environmentally sustainable long-term solution. On top of all of that, it is highly versatile and can be used alone or together with other remediation methods. Despite its advantage, bioattenuation also has several limitations. The remediation process usually takes a longer time compared to an active engineering treatment. It requires detailed site analysis and continuous monitoring to ensure natural processes are effective. In some cases, microbiodegradation may produce toxic byproducts that are more harmful than original contamination. Its effectiveness is also sensitive to environmental conditions such as pH and oxygen level. Additionally, bioattenuation may not be suitable for the complex geological site and can be faced public skepticism with passive treatment approach. In conclusion, bioattenuation or monitored natural attenuation is a significantly rigorous remedial framework that leverages the eccentric capacity of natural ecosystem to mitigate contamination. Successful implementation is predicted upon robust source depletion, high resolution site characterization, and a diligent long-term performance monitoring program. Although not universally applicable, M&A serves as a potent, low-impact methodology essential for a sophisticated and sustainability environmental management strategies.
What if pollution underground could be stopped without digging up the earth? Hidden beneath the surface, there is a technology quietly cleaning contaminated groundwater. This technology is called the permeable reactive barrier. You might be asking, what is a permeable reactive barrier to begin with? Well, according to Camisole et al. In 2013, it is actually a passive remediation system especially designed for the remediation of contaminated groundwater. The technique involves digging a trench in the path of flowing groundwater and filling it with a permeable reactive materials. How is PRB used? It is used to treat contaminated groundwater by filtering out pollutants such as heavy metals, nitrates, and petroleum hydrocarbons. This passive system uses materials like zero-valent iron, activated carbon, and microbes, which makes it cost-effective with low surface disturbance and provides long-term groundwater protection. This is done by studying the direction of groundwater flow and building a trench that will be filled with reactive materials. Then, as the contaminated water naturally flows through the barrier, pollutants will react with the materials and become less harmful. By doing this, the spreading of pollutants into rivers, soil, and drinking sources can be prevented. There are three known methods of executing PRB, and the first one being the reactive media PRB, where it uses zero-valent iron, that is a widely used material, in order to chemically break down chlorinated and industrial contaminants in groundwater. Next, activated carbons are used in an absorption PRB. This works by collecting heavy metals that get stuck at activated carbons network of micropores whilst passing through the barrier. Lastly, a biological PRB that uses microorganisms. Contaminated groundwater containing high nitrate levels from a septic system moves underground towards a nearby water body. A reactive material, such as vegetable oil, is added into the soil through an injection well to form a treatment zone as a food source for the microorganisms. These microorganisms use the nitrate and convert it into harmless nitrogen gas through a process called denitrification. As the groundwater flows through this treatment zone, the nitrate pollution is removed. The reason why PRBs are often used is due to its numerous significant advantages, such as being an energy-efficient method due to its mechanism utilizing the natural groundwater flow, which reduces energy and operational costs. Other than that, it is also an environmentally friendly option because it doesn't require large surface structures as contaminants are being treated underground without disturbing the environment. Lastly, it has a high contaminant removal efficiency, proven in a paper published by Zhao et al. In 2014, where the mixture of reactive materials like zero-valent ions, activated carbons, zeolite, etc. are analyzed. Though this method might seem like a flawless procedure, it has its long-term drawbacks, including the risk of clogging when mineral precipitation or corrosion of products may clog and reduce the permeability of the treatment efficiency over time. Moreover, it requires a long-term monitoring due to its complex well networks, which can lead to high upfront and maintenance costs. Despite its challenges, permeable reactive barriers remain a powerful technology in the fight against groundwater pollution.
Hello everyone, so we are from Group 3. We'll be talking about bioaugmentation and also biostimulations. First, I would like to talk about soil pollutions. Soil pollution happens when harmful waste, chemicals, plastic and detergent contaminate the soil. This can reduce soil fertility, harm microorganisms, and affect human health through the food chain. The main causes are improper waste disposal, industrial waste, and excessive use of pesticides. So, how do we solve these problems? This problem can be solved through bioaugmentations. Bioaugmentation is a bioremediation technique that involves the addition of specific microorganisms into contaminated soil or water to enhance the breakdown and removal of pollutants. These microorganisms use contaminants as a source of energy or nutrient to help degrade harmful substances more efficiently. So how does this treatment happen? The first step is site assessment. In this stage, the contaminated area is analyzed to identify the types and concentrations of pollutants present. Environmental conditions such as pH, temperature, and oxygen levels are also examined because these factors affect microbial activity. The second step is selection of microorganisms. Suitable microorganisms that are capable of degrading the pollutants are chosen. Next is isolation and culturing. The selected microorganisms are grown under laboratory conditions to increase their populations before being introduced into the contaminated site. The fourth step is preparation of contaminated site. conditions of the site optimized to support the microbial growth. This may involve adjusting pH, supplying oxygens, or adding nutrients. The fifth step is inoculations, where the culture of microorganisms are introduced into the contaminated soil or wastewater, and these microorganisms then begin their activity in degrading the pollutants. The sixth step is biodegradation process. The microorganism use the pollutants as a source of energy and nutrient, converting them into simpler and safer substances such as carbon dioxide, water, and biomass. The seventh step is monitoring and maintenance. Researchers regularly monitor microbial growth, pollutant reductions, and environmental conditions to ensure the treatment is effective. Finally, the treatment process is completed when the pollutant concentration reaches a safe and acceptable levels. This is an example of bioaugmentation, which degradations of xenobiotic in wastewater treatment. It is antibiotic pollution that causes environmental risk. In this treatment, Bacillus paromycoides is immobilized into the biochar matrix. It was added to cleanse wastewater contaminated with sulfamethoxazole, SMS, and zinc. Now let's move on to the advantages and disadvantages of bioaugmentations. First, the advantages: targeted degradation. Specialized strains are introduced to degrade highly complex toxic pollutants that cannot be degraded by native microbes. Secondly, eco-friendly, natural and sustainable process, which it can convert hazardous waste into harmless product. And thirdly, cost-efficient operation because it's lower capital and labor cost compared to mechanical excavations or chemical treatment. Next, the disadvantages. First, the low survival, which introduced microbes often died due to the local predators, phages, and harsh environment. Secondly, toxic intermediates, risk of incomplete degradations and create more toxic byproducts than the original pollutants. And lastly, heavy metal limits. Microbe cannot degrade heavy metals. It requires a complex hybrid method with phytoremediation. Now let's move on to biostimulation. Biostimulation is bioremediation strategy that rejuvenates contaminated soil by incorporating nutrients or stimulants to enhance the metabolic activity of indigenous microorganisms, thereby increasing the degradations of environmental contaminants. So how does this treatment happen? This treatment happens by first adding nutrients such as nitrogen, phosphorus, and also adding fertilizer such as ammonium nitrate and phosphate salts. With adding nutrients, it can increase the enzyme productions and accelerate the pollutant breakdown. Secondly, oxygen supply. Techniques such as air injections, air spudging, and also soil aeration systems, bioventing, and oxygen-releasing compounds such as calcium peroxide. And then move on to the pH adjustment, such as adding lime to raise the pH if it too acidic, and adding sulfur compound to lower the pH if too alkaline. Then move on to moisture control. It's controlled by irrigations by adding water, and also drainage system by removing the excess water. Lastly, the electron acceptors, such as nitrate and also sulfate. This is the example of biostimulation that have been done. It is a major oil spill event, which is Exxon Valdez spill 1989. In these cases, applying Anipol EAP22 and other fertilizers on the Alaskan shorelines, which can help to accelerate the shore oil degradation after major marine oil spills. Now let's move on to the advantages and disadvantages of biostimulation. The advantages of biostimulation is first, absolute adaptations, which native microbes already acclimate to regional environments. Secondly, high public and regulatory acceptance, which eliminating anxieties regarding release of genetic modified organisms, GMOs, and also avoid creating competitions of resources with indigenous strains in wild ecologies. Now let's move on to the disadvantages. Firstly, overstimulation, which excessive dosing of stimulants can cause overgrowth of non-target microbial biomass. And secondly, it can slow startup phase. The native bacteria often begins in a highly depleted state due to toxicity of initial pollutants. These are the differences between bioaugmentations and biostimulations. Bioaugmentations add specialized microbial strain, while biostimulation add growth amendment to trigger microbial activities. As in aspect infill feasibility, bioamendment failure might due to, while biostimulations widely used in large open earth sites. From the aspect of biological challenges, poor cell survival potential bioinvasions issue might happen on bioaugmentation, while biostimulation ecosystem imbalance happen, which is secondary pollutions. These are the reference lists that we use.
Did you know that petroleum spills can remain trapped in soil for years and slowly contaminate groundwater? This is a serious environmental issue because contaminated soil can act as a continuous pollution source, and once groundwater is affected, it becomes dangerous since it is used as a drinking water resource. Conventional cleanup methods such as excavation are often expensive and time-consuming. This is why bioremediation is used as an alternative solution. It is an environmentally friendly approach that uses microorganisms to degrade pollutants. More specifically, in-situ bioremediation treats contaminant directly at the original site without removing the soil, making it more cost-effective by reducing operational and transportation costs. One important in-situ method is bioventing. Bioventing is a technique used to treat contaminated soil in the unsaturated zone, also known as the vadose zone, which is the soil above the groundwater table. Bioventing works by supplying a controlled flow of air or oxygen into the soil to stimulate indigenous aerobic microorganisms. These microorganisms naturally break down the contaminants into carbon dioxide and water. A common example is the treatment of leaking underground storage tank at industrial sites, where fuel leaks into vadose zone. In this situation, oxygen is injected into the soil to enhance natural microbial degradation at the site. The main treatment purpose of bioventing is to enhance natural biodegradation processes by supplying oxygen. At the same time, it prevents contaminants from moving deeper into the soil. Moving on to process, the first step is well installation. Bioventing wells are installed from the ground surface into the vadose zone. These wells deliver air directly into contaminated soil. Next is air injection. An air pump supplies oxygen into the soil at low flow rates, typically between 1 to 100 liters per minute per well, to support aerobic microbial activity. Bioventing can operate through air injection or air extraction, where extracted vapors require treatment using activated carbon filters. To enhance microbial activity, nutrients such as nitrogen and phosphorus may be added through biostimulation under optimal conditions. The oxygen then disperses through soil pores and reach the native microorganisms, which then degrade the contaminants into carbon dioxide and water. The advantages of bioventing include stimulating indigenous microorganisms to naturally degrade petroleum contaminants. It also enhances microbial degradation activity and helps reduce the spread of heavy metal pollutants, resulting in cleaner soil condition. However, bioventing has some limitations. It is less effective in soils with low permeability, low moisture content, or low temperature. These conditions reduce microbial activity and slow down the remediation process. In conclusion, bioventing is an effective in-situ bioremediation method that uses oxygen to stimulate aerobic microorganisms. In practice, bioventing is often combined with other treatment methods such as biostimulation to improve overall remediation efficiency. Bioventing is a promising method because it is a cost-effective and environmentally friendly alternative to conventional methods.